after having understood how to calculate irreversible work, the equation is P delta V minus P external into delta V, right? Let us try and understand what would happen if we perform compression of a gas from a volume Vi to Vf, but not in single step, but in a few irreversible steps. Let us understand this. I'm going to put a graph here. Right. This is again a pressure volume graph, and you must know that pressure volume graph, area under pressure volume graph can be used to calculate work done. Yeah? Now, let us have Vi here, and this is Vf. We start with volume Vi, and right? This is the volume of a gas initially. Now, we don't accomplish the process in a single step, but let's say we increase the pressure. We increase the pressure a little, because of which the volume decreases. Step 1 is irreversible, and in step 1 the pressure remained constant. So this would be like the internal pressure of gas is 2 atm. We have to make that pressure 4 atm so that the volume is halved. We want to make volume halved. Pressure of gas is 2 atm. So what we do is, like, initially we keep external pressure as, let's say, 2.5. So the piston would go in, right? And then the internal pressure of gas would become 2.5 atm, equilibrium is established. Now, we again increase the pressure, and once again the volume decreases. We again increase the pressure, volume once again decreases. We again increase the pressure, and finally we reach the external pressure, volume decreases. Volume decreases further, and we have reached our final volume. What is this pressure now? This pressure is the P external pressure, which was, when we perform our single step irreversible process of compression, right from the beginning we will have to keep our external pressure this. But here we start increasing the pressure in steps. Allow the gas to attain equilibrium, then once again we increase the pressure, again then the volume decreases, equilibrium is established. So finally we have to reach P external so that the volume becomes Vf. But if you are carrying out the process in a single step, then the process would go like this. The process would be going like this. Do you understand this? If we perform the work in a single process, single step, what would be it? At Vi, the pressure has to be kept P external. Then we keep the pressure constant, and then the gas gets compressed to its final volume, single step. What is the area under graph? This full thing is area under graph. That would be the work done. However, when we do it in steps, look at this. The work done in first step, what is it? Pay attention. The work done in first step is this. This is W1. Then in second step it is this, W2. Third step it is this, W3. So we have W1 here. This is W2. This is W3. And this is W4. Clear or no? So the total work done, work total, is equal to W1 plus W2 plus W3 plus W4. In other words, work done, total work done is equal to minus P external into delta V for processes going from step 1 to step 4. Here I can say step N. If the process is accomplished in N steps, then for every step we have to calculate minus P external into delta V, and it goes from step 1 to step 4. Is that okay? Clear?
Then, can we say that work done by force in a single step is more?
Yes. That is what I am coming to. I want to explain the difference between the two. I want you to understand the difference between them. So now that you are compressing a gas, so who is doing work? You are doing work. Because we are doing work, we are compressing a gas and taking it from volume V1 to Vf or V1 to V2, whatever. So we have to do work on it. We're doing work. We're spending energy. So where would it be more convenient? Where would you spend less energy, doing it in steps or doing it in a single go? In a single go, you'll have to do more work, right? So you'll be spending more energy. But if you're doing it in steps, the area under graph is less. You will be spending less energy. So ideally, pay attention. When you're doing it in steps, the colored portion that you see here is the work done. You find out the area under all these and it'll be work done. But if you're doing it in single step, you will have to do this work plus some extra work which is shown by this part here. This is the extra work that you'll have to do, more work that you have to do if you're doing it in a single go. So what is better? When you spend less energy doing the same work, you have to do it in steps. So a simple thing is, this is the extra work that you do. Done when compression is accomplished in single step. And we say, no, this is, I think, your compression in more than one steps is always better. So now I would start getting greedy over this, right? And I would say, no, I don't even want to do this work. How can I reduce my work now? So you would say, then do it in even more steps. Instead of doing 4 steps, take 8 steps. And work will further get reduced. Instead of 8, then you do 16 steps. And the work would be further reduced. Then I would say, no, I want minimum work. Minimum possible work. Then they say, perform it in infinite steps. Perform the same work in infinite steps. Isn't it? If you perform the same work in infinite steps, that'd be the minimum work done. So what are they asking us to do? They're asking us to carry out the whole compression in a reversible manner. Because when anything is carried out in infinite steps, it becomes a reversible process. Do you understand this? So if you ask me, no, we want to accomplish the compression of gas from VI to VF, but we want to know what is the minimum work that can be done here. We want to know the lower limit. We don't want to do a bit of extra work. We just want to do the minimum work. Then I would say, carry out the work in reversible manner. By calculating reversible work, you know what the bottom line is. So if the bottom line is 5 joules and if you're doing 10 joules, then I would say still there is some room for improvement in your work. You can still reduce the work because the lower limit is 5. That's the minimum. Do you understand this? So you get an idea about what lower limit or what upper limit is. By which, when you are when you're doing any process, you can try to accomplish that process with minimum work or maximum efficiency. That is why we need to know what reversible work is. In each case, compression as well as in expansion. Do you understand this? So now I am going to show you how to calculate this in infinite steps. How do you calculate this? Yes, yes.
Sir, you said that when you do infinite steps, the reaction becomes reversible.
The process becomes reversible. This compression then is called reversible process, because by definition, what is reversible process? A process which is accomplished at an infinitesimal slow pace. What is an infinitesimal slow pace? A process which involves infinite microscopic stages. That's reversible. So here, I just wanted to give you an idea about when you increase the number of steps in compression, your work will decrease. So if you want to keep on reducing the work done, doing the same process, for the same process, if you want to keep on reducing your work, increase your steps. Try to perform the same work in more than one step. And towards the end, if you want to know the bottom line, the minimum work that can be done in any process, you have to calculate reversible work. So in any compression, if you ask me what is the minimum work that one has to do, I would say calculate reversible work for compression. That's the minimum work you have. Okay? So do you understand the concept of reversible? It's very important to understand the concept first. And it's very important to get an idea about, now this is going to be accomplished in infinite steps. Okay? And we would try to get a graph of how the work can be calculated in infinite steps. So now we're trying to do the same compression of gas from Vi to Vf in infinite steps. Right? So here, consider compression of an ideal gas from initial volume Vi to a final volume Vf in infinite steps. So we are doing the same compression in infinite steps, not one, infinite. Okay. Let us do this now. Here, from Vi to Vf, we're doing this in infinite steps. Okay. Work done at every microscopic stage for a very small change in volume is TW. Sorry, a very small change in volume, dV is dW. So for a very small change of volume dV, the work done is dW. Okay? Now, dW is equal to the step in which volume changed by dV is actually an irreversible step. The microscopic step where volume changed only by dV is an irreversible step, where pressure remains constant. And for that, we say it's minus P external into dV. Right? in order to calculate the full work done, what we do is total work done is called W reversible, and that is equal to, you add up the infinite values of dW. There are infinite dW values and you'll have to add up. So there you don't put summation then. When you do add up like that, you do the integration. And integration from volume VI to VF, and we add up all dWs. And this should be equal to minus VI to VF P external into dV. All okay? Clear? Now pay attention. Here we find that at every microscopic stage, P external here will be equal to P internal plus dP, where dP is like very, very small value because external pressure has to be more than internal pressure. So P external would be P internal plus dP, a very small value, right? This is for compression. And also P external can be P internal minus dP for expansion. So when expansion is taking place, P external will be less. Therefore, in general, P external is equal to P internal plus or minus dP. It can be plus or minus dP for any process. Okay. Okay. When you are compressing a gas in a reversible process, at every microscopic stage, your external pressure has to be slightly more than internal pressure. So your external pressure should be internal pressure plus dP. And when you are when the expansion is taking place, when gas is doing work and it is getting expanded, your external pressure has to be less. So your external pressure would be internal pressure of gas minus dP. In general, for expansion or compression, it will be plus or minus dP. Clear? Okay. Now pay attention. Therefore, the reversible work that we have to calculate is equal to VI to VF negative V internal plus or minus dP into dV. Instead of P external, I am putting P internal plus or minus dP. All good? Now, if you open this up, it will be P internal into dV, integration, plus or minus integration of dP dV. But dP dV are two very, very small values and they can be neglected. So here, therefore, W reversible now can be given as VI to VF P internal into dV, P internal into dV. Is that okay? Clear? समझ में आवे जा? P internal into dV. Now pay attention. Here we know that P internal is equal to pressure of gas, A minus, and pressure of gas is equal to nRT by V. Why? Because for ideal gas, PV is equal to nRT. So P is equal to nRT by V. Can we put this as now? W reversible is equal to VI to VF negative sign nRT by V dV. Can we do that? It's P is equal to nRT by V. Now here N is number of moles of gas and R is equal to gas constant. Both of these are constants. Also, if process is isothermal, T will also be constant.
So what is that given?
Isothermal is when temperature throughout the process remains constant. The process is isothermal, T is constant, and therefore W reversible is equal to minus nRT VI to VF 1 upon V dV. What is 1 upon V dV integration? ln V? It's ln V. So we put minus nRT into ln V. The limits are VI to VF. Limits of VI and VF. So now, what would that be? Minus nRT ln VF minus ln VI. You know, ln A minus ln B is ln A upon B. ln A minus ln B. So that's natural log. ln is natural log to the base E. So what is that? ln A minus ln B is equal to ln A by B. And ln A into ln B would be ln A plus B. Here? So minus hoy to division, plus hoy to multiplication. So now I can put it like this. Minus nRT ln VF by VI. Therefore, W reversible is equal to, pay attention, I want to remove this ln and put a log. ln is log to the base E and log is to the base 10. I want to convert ln into log. whenever you want to convert ln into log, because for calculations we would use log only. So we would have to multiply the whole thing with 2.30 so 2.303 nRT log VF by VI.
Okay, so log में easy for the calculation.
We would be doing this. So this is the first part. Pay attention. Here we have W reversible is equal to minus 2.303 nRT log VF upon VI. Is this okay, clear? समझ में आएगा बराबर? All right. You also know that for an ideal gas at constant temperature, for an ideal gas at constant temperature, P is inversely related to V. This is Boyle's law. And therefore, VF upon VI, because P is inversely related, should be equal to PI by PF. And therefore, the above equation that we have can also be written as W is equal to minus 2.303 into nRT log PI upon PF. This is also one of the equations that you can use. So for reversible work, the equations that we have are minus 2.303 nRT log PI by PF or VF by VI. Now, if you talk about how the graph looks like, graph would look like this when you are doing. This is VI and this is VF. This is pressure. Your graph has to go like this. Your graph goes like this. Clear? This is like your VI to VF. Pressure keeps on increasing because you're doing compression. All okay? And had it been, and this is the external pressure that finally you arrive at. Had it been an irreversible compression, what would be the graph looking like? Had it been a irreversible single stage compression, it would have been like this. This is what we consider as, this is the extra work. Extra work done when compression is done or accomplished.
So,
In one step. Yeah. This is the reversible work. This is W reversible. So W reversible is very, very less as compared to during compression as compared to when the same work is done in one step. Right? If you want to compare it with work done in more than one steps, it would be something like this. Your graph would probably go like this. So reversible graph would go like this. It still would have lesser one, right? So, yeah. This is what we have now, the graph and everything. So what is free expansion? That is what we talk about. So, expansion of an ideal gas when P external is equal to 0 is referred to as free expansion. This is also considered as expansion of an ideal gas in vacuum. When externally there is vacuum, inside gas હોય એટલે vacuum ના જ હોય. એટલે બહાર vacuum હોય. So when gas is subjected to a cylinder and external pressure is 0. You have a piston, something like this you have to think about. It is something like this.
અંદર કોઈ પ્રેશર છે અને બહાર જરા પ્રેશર નથી તો પિસ્ટન આમ બહાર ના
હા એ જ કરવું પડે, but then that is what is going to happen. But that is why we try to understand gas, what exactly would be the work done. So what is free expansion when external pressure is 0? It is expanding in vacuum. So what is the work done in free expansion? Work reversible, which is also equal to work irreversible, and this should be equal to 0. Why? Because when P external is 0, everything has to be 0. So, in free expansion of an ideal gas, work done, irrespective of what path is taken by the system, reversible or irreversible, it has to be 0. Clear? Now, we're doing graphical representation of reversible and irreversible expansion. So we're doing graphical representation of reversible and irreversible expansion. Reversible and irreversible expansion. Now, you have to understand one thing, that when we are doing expansion, let me give you some basic idea about what we're doing now. This is, let's say, our cylinder. Okay, and then we have a piston here. And then there is this gas inside. The pressure of gas is P internal and volume is VI. The pressure outside is P external and P external is less than P internal. So, the gas is expanding. The gas is expanding. Now, in case of, let's talk in terms of some values. Suppose this is 2 atm inside. The pressure inside is, let's say, 2 atm. For irreversible expansion, single stage expansion, the pressure outside could be maybe, in reversible case, it can be maybe 1 atm. So in a single go, the volume will get doubled for the gas and pressure will become half and will become 1 atm, and that's it. But if you want to carry out a reversible process, in that case what you have to do is P external will have to be, let's say, 1.999. The piston moves out a little and then equilibrium. Then we change the pressure to 1.998. This is just an example. You keep on decreasing the pressure at an infinitesimal, the pressure is changed infinitesimally, which means the decrease is very, very less. So in that case, the process becomes more or less reversible. And so we understand one thing, that during expansion, what do we conclude? P external is the maximum possible value in reversible process. So when you're talking about a reversible process, you can see that here P external could be 1 atm, but when you're doing it in reversible way, the P external is the maximum possible value that you have to put. And therefore, P external is much higher than, in reversible than in irreversible. So when we talk about how to plot a graph, let me show you how this works. We're doing expansion, VI to VF, right? Let's say this is P external. Let's say this is P external. So at VI, we will have in irreversible process, we have it like this. And then it goes right up to this area under graph. What does this work? This is W irreversible. Clear? But you know that in reversible process, you find that the external pressure would be much higher. So let's say your external pressure, let us assume that your external pressure is here. Right? And from here on, as as the gas expands from Vi to Vf, the pressure continuously drops. This is extra work done when expansion is carried out reversing. So what do we conclude then? We conclude that, what do we conclude? We conclude that W reversible is equal to W maximum during expansion and W reversible is equal to W minimum during compression. Do you understand this? Are you getting it? So now we move on to the laws of thermodynamics. So we're doing laws of thermodynamics. There's this zeroth law, which is not really mentioned, but it's a very basic law. Law is very simple if you want to understand it with a diagram. Let's say we have three bodies, A, C, and B. Right? We have three bodies. And they are, A is in thermal equilibrium with B. What do we mean by thermal equilibrium? The heat going from A to B and heat going from B to A is same, which otherwise would mean they are at same temperature. So if two different bodies, here we have A and C, which are simultaneously in equilibrium with a third body, which is your B. If two different bodies are in simultaneous thermal equilibrium with a third body, then they are in thermal equilibrium with each other as well. Samajh aayega barabar? So that's zeroth law. It's very, very, very basic law, right? If two different bodies are in thermal equilibrium with a third body, then they are in thermal equilibrium with each other as well, is the statement. Will you be able to do that? I'm not writing the statement. Right? All right. Then we have the first law. First law of thermodynamics. This is also called FLOT. First law of thermodynamics is in short, written as FLOT. So every time I write first law of thermodynamics, you just write FLOT, as per FLOT. And then, so that's the same thing. All right. Here we say, this was given by Robert Mayer and Helmholtz. Given by Robert Mayer and Helmholtz. This law is nothing but, it's the law of conservation of energy. Energy can neither be created nor destroyed. It can only be transformed. So I'm not writing the full thing once again. You have it in the notes also. I'm just writing energy of universe remains constant. You have it in the notes also. And then the statement given is like energy can neither be created nor destroyed. It can only be transferred from one to another. Right? Now we try to get the mathematical form. So here we say that let U1 be the initial internal energy of a system. Q is the heat given to the system, and W is the work done on the system. Clear? U2 is the final internal energy of a system. Therefore, U2 is equal to initial energy plus heat gain plus work done. And therefore, U2 minus U1 is equal to Q plus W, or delta U is equal to Q plus W. This is the mathematical form of first law. However, it can have some variations, a few here and there. So W is equal to minus P delta V. P external into delta V. Therefore, delta U is equal to Q minus P external into delta V. Right? And therefore, Q is equal to delta U plus P delta V. This is one more P external into delta V or P delta V. It's just, these are two important mathematical forms of first law. Right? Now we try to review the mathematical form of first law under different conditions. So we try to figure out what would happen to the equation under different conditions, right? So let us go through different processes. Let us talk about the first process, isothermal process. In isothermal process, delta U will always be zero because internal energy is a function of temperature. Internal energy of a system changes only if temperature changes for an ideal gas. So delta U is equal to zero because it is isothermal where temperature is constant. So if temperature doesn't change, internal energy will also not change. So delta U is equal to zero because delta T is equal to zero. From FLOT, zero is equal to Q plus W. Therefore, W is equal to minus Q or Q is equal to minus W, whatever it be. So for isothermal process, they say all the work done on the system will be released in form of heat. Or the other way around, all the heat which is given to the system will be utilized by system for doing work. So when heat is plus, it is given to the system. So when heat is given to the system, all the heat that system receives, it will be utilizing it for doing work, because work is negative, which means system will do work and utilize it. Internal energy will not change. Okay, the next process. P external is equal to 0. A process in which P external is taken as 0. In such a case, W is equal to minus P external into delta V will be equal to 0. Therefore, delta U is equal to Q. Delta U will be equal to Q.
Work done be 0.
Yeah, work done is 0. So from first law of thermodynamics, which is delta U plus Q, delta U is equal to Q plus W, first law of thermodynamics. So what would happen? Your W is 0, so delta U is equal to Q, right? Yeah. The third, adiabatic process. In adiabatic process, Q is 0. Therefore, from FLOT, delta U is equal to W adiabatic, work done under adiabatic conditions.
So what is adiabatic?
Adiabatic is a process in which there is no heat which is exchanged between system and surroundings. So system and surroundings are not able to exchange any heat in between them. Which means Q is the heat exchange between system and surroundings is 0. I've already sent Thermo 1. Ideally, you should go through that. Yeah, you have to properly go through that video.
Couldn't school exams.
After they get done, both these videos, today's video as well as the first video, please go through them properly, write down all the important equations, prepare properly and come with your doubts. Also try to finish off your at least level 1 of chemical bonding module and level 2 at least half. So next time we can spend some time for doing numericals from this part that we've done. I've got a list. And because thermodynamics and chemical bonding, they are in different modules, bring both the modules. They're in different modules. Yeah? The fourth part is isochoric process. This is a process in which volume of a gas will not change. Delta V is 0 for any isochoric process. Therefore, from first law of thermodynamics, delta U is equal to QV minus P external into delta V. But delta V is 0.
Delta U is equal to
And QV is heat exchanged between system and surroundings at constant volume. Therefore, we arrive at one very important thing, QV, and this is how we define delta U. This means, therefore, change in internal energy of a system is equal to heat gained or lost by the system at constant volume. All right? So this is the first part theory done. Next time we'll start solving numericals from this part.